one is to look at something called as Stokes Stokes-Einstein relation. This is applicable to something called as Brownian particles. Okay, as I was mentioning in the previous class, this is one of the widely used relationship for or relation for finding out particle size data. Okay, if you have a particle dispersed in a fluid, if you want to measure its diffusivity or if you want to measure its particle size, okay, this is one of the widely used relation. Okay, we're going to talk something about phoresis. Okay, which basically refers to if you have a particle and in a fluid and if you set it to motion, okay, motion of a particle in a fluid, to what is called as phoresis, and you can set a particle into motion by using external field, right? And either you could use something called as a concentration gradients, okay, or you could use thermal field or thermal gradients, or I can use some other force. Okay, it could be electrical forces, you know, or magnetic forces, right? So if you set the particle into motion by using, you know, by exploiting the concentration gradient, this is something called as a diffusophoresis. Okay, if you use thermal fields, something called as thermophoresis. Okay, and if you use electrical field, it's what is called as a electophoresis, right? Okay, so we're going to look at some aspects of, you know, phoresis. Okay, this is what is going to be the plan for today. So I'm just going to start by showing you again a movie which I showed in the last class. Okay, so this is what has been done is that, you know, the white dots that you see, these are particles. Okay, these are something called as fluorescent particles. Okay, when people use fluorescent particles, the idea is that if you use a regular optical microscope, okay, which works by using the white light, you can see objects up to about a micrometer or larger. Okay, of course you can also look at things that are smaller than micrometer, but you can't resolve it. Okay, you can't get a good image by using optical microscope. What people do is they use fluorescent particles, okay, by which I can actually push the limit of microscopy. I can also look at things that are much smaller than a micrometer size. You can even look at things that are 200 nanometers, 300 nanometers. Okay, so this is sub-micrometer particle, and these are fluorescent particles, and white dots, as I said, these are spherical particles dispersed in a fluid. Nothing is being done. All that is done is you're just putting the particles in a fluid and you're just watching, you know, with a microscope. Okay, and what you see is that particles are moving, right? This is without the influence of any external force. They're just moving by themselves. Okay, and if you can see, there is no particular direction in which the particles move, right? They're just moving chaotically. Okay, and that is because, okay, so you have molecules of the fluid around each of these particles, and there's a bombardment of the fluid molecules with the particle. Okay, and depending upon the bombardment, it will just move in some random direction. Okay, it could be in x, y, z, any direction. Okay, now such a chaotic motion, okay, is something called as Brownian motion, right? Okay, such a chaotic motion, okay, such a motion which is because of bombardment of particles, okay, with the molecules of the fluid okay, is what is called as a Brownian motion. Okay. So, the particles really do not move in any particular direction, okay. This is a random motion, okay, which is purely existing because there are molecules and atoms that constitute the fluid in which these particles are dispersed. Okay. Now, from yesterday's lecture, we know that whenever we have a relative motion between the particle and the fluid, okay, there is going to be something called as a drag force, right. Okay. We also said it is also called as frictional force, okay. You can also call it as hydrodynamic drag force, right. Now, so you can think about, of course, we already know what this hydrodynamic force is, right. Yesterday we already wrote up an expression for it, right. But the other way of thinking about this, drag force is going to be, you can actually bring in the concept of friction factor, okay. So in this case, CD is something called as what was that? Oh, it's on, no? Oh, maybe is that? Yeah. Okay. Okay, CD is something called as a drag coefficient, and it is defined something like this. Okay. Drag force divided by some area over density times some velocity head. Do you recognize this formula? Some similarity that you may have seen in the previous lectures? So, if you look at this carefully, this is of the form, your friction factor, was something like wall shear stress divided by, some velocity square, right. That's something like that, right. That's what it was. It was density, okay, multiplied by the velocity head, and there was a wall shear stress. Okay. Now, your shear stress is actually force per unit area, right. So, F in this is what is called as a drag force, and your AP is something called as a projected area. Okay. And this projected area, what is being done is, if you have a spherical particle, okay, if that is fixed in space, and if there is a liquid moving over it, okay, now what you do is you look in the direction perpendicular to the flow, okay, what is that area that you see, okay. If you have a spherical particle, if I look perpendicular to the flow, what I would see is a circle, right. So, your AP is going to be area of the circle that you see, that is your projected area, okay. And of course, rho is the density of the fluid, and u naught is the velocity with which your particle is moving in the fluid, okay. Now, a lot of people have done, so now again we did this calculation yesterday. If you take the Reynolds number for the particle, we said it's going to be a diameter of the particle times some average velocity, okay, times rho, the density of the fluid, divided by mu, right. And it turns out that because of the particle dimension that we are working with, this is going to be much less than 1, right. Yesterday we calculated this is going to be of the order of 10 power minus 6, okay. Now, whenever you are working under conditions where the Reynolds numbers are much less than 1, we said that comes into some kind of a low Reynolds number flows or the laminar flows, right. And people have done a lot of experiments, and they have found that the CD for the Reynolds number much less than 1 goes as 24 divided by Reynolds number, okay. Now, what I can do is I can take this relationship, okay, and substitute for CD in this equation. I know what is the average velocity, okay. I know what is rho, and as I said, your AP is the projected area, which is pi rp square. If you substitute that, can you just let me know what your FD is? Can you just do this simple math? So you substitute for CD as 24 by Reynolds number, and Reynolds number is given by this, okay, and so your AP is pi RP square, or if you want to is pi dP square by 4, right? Okay, if you do that, can you guys let me know what FD is? Right, so you basically recover back the Stokes law, right? That's what we had done, right? Now, if this is your velocity with which the particle is moving, okay? If I know what is the average displacement, okay, over time is what is your average velocity, right? Now I have a movie in which the particles are moving, okay? I can track the particles in every frame of the video. I can get their location, okay, and therefore I have a way of calculating what is the average displacement of the particle, okay, per unit time is going to give me what is the velocity with which the particles are moving, right? Now, if I want to calculate, okay, what is, so now that I know that there's a particle that is moving, there's a drag force, so I want to calculate what is the energy that is required to move the particle. Okay, so how do I calculate that? I want to calculate what is the energy that is required to move the particle. Right? So the work that has to be done for moving the particle, or the energy that is required to move the particle, is essentially your Fd times x bar, right? Your force multiplied by distance, and we know that it is moving, it has moved an average distance x bar. Now, so this energy that is required to move the particle, where does it come from? It comes from the thermal energy, right? Your kBT. So we said that the reason why the particles are moving is because the solvent molecules are hitting the particle, okay? And why do solvent molecules are hitting the particle? Because your fluid is at a finite temperature, okay? Whenever you have a finite temperature, so you're going to have, every molecule is going to be associated with a energy which is given by Boltzmann constant times your temperature, okay? Therefore, the energy that is required to move the particle, which is Fd times x bar, actually comes from the thermal energy, okay? Now, what I can do is I can substitute for Fd is 6 pi mu, u naught is x bar divided by T, okay, times Rp times x bar is equal to kBT, right? I can rearrange this and I can write it as x bar square by time is equal to kBT divided by 6 pi mu Rp, right? Yeah, and this is d, which is the diffusivity of the particles in the fluid, okay, and it should have dimensions of meter square per time, right, meter square per second, okay. Therefore, your diffusivity of the particle is equal to kBt divided by 6 pi mu times Rp. This is what is called as a Stokes-Einstein relation. Okay. This is a simple arguments of getting this equation, but there are other ways of doing this. Okay. So all that we did was we said that there's a particle is in motion, and because of which there's going to be a drag force. Okay. And we said that this is basically Stokes drag because of the fact that the Reynolds numbers comes out to be much less than 1. Okay. And the energy associated with moving the particle is your drag force times the average displacement. Okay. And that has to come from the thermal energy. Just by equating that, you will get a relationship between the diffusivity of the particles in the fluid and the thermal energy, and this is some kind of a friction factor. Okay. Okay. People also write this as kBt divided by F, okay, friction factor, which is basically 6 pi mu Rp. Yeah. Yeah. Go ahead. Yes. Why is it not the case? So all that we are saying is, I mean, okay, so this is going to be, I would say this is kind of more of an idealized case, right? Okay, and it turns out that of course, if you take particles which could be rough, for example, okay, if the particle is kind of set into rotation because of this bombardment, in such cases you would have to worry about accounting those cases. But if you take like say rigid spheres, smooth spheres, of course there are some kind of assumptions where you can use this, but this is typically applied for rigid particles, okay, and the particles have to be in colloidal size range, of course, because they have to exhibit Brownian motion, and of course this is for a smoother surface and things like that. Okay, of course in real systems but it turns out that this kind of this equation typically is valid for a lot of colloid that people use in everyday experiments or life. So yeah. Okay, so now that we know that there is a relationship that exists between your diffusivity and kBt and the friction factor, what someone called John Perrin, okay, did was he basically did the very first experiments, okay, on quantifying Brownian motion. Okay, this happened around 1920s. Okay, and all he did was he basically had this video of the particles moving in a fluid. Okay, and he tracked the particles. So what he did is, this is the frame of the movie that I've got. I have one particle here, and what I do is at some, if this is time t, okay, I take at some other time interval, say t plus delta t, I look at where the particle is. Okay, now I look at another frame, say t plus 2 times delta t, I look at where the particle is. Okay, so in the end what he did was he basically came up with a picture of the location of particle as a function of time, right? So it was basically exhibiting some chaotic motion. So all that he had was he had some information about the time frame, okay, that is the distance, he had information about what is the delta t between the two frames that he was considering, and of course he had tracked the particle. That means he had access to the particle position as a function of time. Okay, so once he did that, so he calculated what is called as a mean square displacement. Okay, and that mean square displacement is given by something like this. Okay, all you have to do is, if you have basically tracked the particle for a time t, okay, if you have observed it for enough time, so what you did is your x at time ti plus t minus x at time ti whole square plus y at ti plus t minus y at Ti whole square, okay, right, divided by n is the mean square displacement. Okay, all that you do is you basically know the positions, right? Okay, and if I have, like, say I have taken 10 frames, right, I know the distance it travels in every frame. Okay, so that's your mean square displacement. Now that the mean square displacement could be measured by experiment, what he did is he made use of the theory of Brownian motion that Einstein had developed, okay, which basically said that if you observe a particle for long enough time, that is for t going to infinity, okay, your mean square displacement, okay, goes as 6 times dt, where t is your observation time and d is the diffusivity of the particles. Okay. Now, because he was able to measure this, okay, Perrin was able to measure it, he can actually calculate what is diffusivity. Okay. Now, your Stokes-Einstein relationship is kBt divided by 6 pi mu rp. Okay. Now, he was careful enough to pick particles of exactly same size, okay, because he had access to an electron microscope. He basically took particles which are about 0.53 micrometer in radius. He was able to work with well characterized particles, so he knew rp, okay, and because he could do Brownian motion experiments, he was able to calculate d, that is known now. Okay, and of course he used water as a fluid in which the particles were put. Okay, he knew the viscosity. From this, what he did is he calculated kb, okay, the Boltzmann constant. Okay, and we know that Boltzmann constant is basically your universal gas constant divided by the Avogadro number. Okay, that's how he was basically able to calculate what is the Avogadro number, and the number that he got from his experiments, as I said yesterday, was very close to 6.023 into 10 power 23. Okay, so this is, yeah, go ahead. Which one? The mean square displacement. So if you look at the video, right, so you had particles, all the particles were kind of exhibiting some motion, right? Now what I can do is I can actually go and pick one particle. I can look at that particle as a function of time. Okay, now in each frame I locate the same particle. Okay, now so therefore what I can do is for every frame I can associate a location, right, which is basically your x comma y, okay, because you are looking at in 2 dimensions. Okay, now once I have access to the position of the particle, okay, and if I know what is the time frame that I'm basically considering from the video, right, I can choose that, hey, I have a, like, say, video for say 5 minutes, I'm going to look at every 5 seconds, you know, what is the location. So if I have information, I can basically back calculate what is the mean square displacement. Yeah. Okay, so so as I said, right, this is a useful equation, so which you should remember, you know, and it's kind of used in a lot of commercial instrument that people buy for measuring particle sizes. The basic equation that basically goes into the calculation of the sizes is this particular equation. Okay, they will have some way of measuring diffusivity. Okay, it could be done either, you know, if you use a microscope, there will be some algorithm by which I can actually calculate the mean square displacement, from which I can calculate d. Okay, I plug in that d here, okay, and I can calculate, you know, rp, which is the size of the particle, right? Or there are other ways of getting d. Okay, and there are some instruments where what people do is they measure, if I have a particle in a fluid, you shine a laser light, okay, because the particle is moving, okay, you detect what is called as a scattered intensity, okay, and because of the chaotic motion of the particle, the laser intensity also fluctuates, okay, and from that fluctuation there's another way of back calculating your d. Okay, so no matter what the instrument is, okay, whether you get d from the fluctuations of the scattered intensity or by using some kind of particle tracking, in the end the size of the particle is basically determined by using Stokes-Einstein relationship. Okay, so we'll move on to the next topic, which is phoresis. Okay, in specific we are going to talk about something called as electrophoresis. Okay. Now, for electrophoresis, what you do is, so all of you know, if you have, like, say I have a cell, say if I have a cathode, for example, okay, and an anode, right. Now, if you have ions in solution, okay, if you have, like, say positively charged ions or negatively charged ions in solution, like this is, say this is going to be your a fluid, right. Now, we know that, the moment you apply some kind of a voltage difference, right, a potential difference, we know that, ions are going to move, right. Now, of course, the positive charged ions are going to move towards the cathode, right, it's going to be moving this way, and negative charge is going to be, if this is your negative and positive, right. So, negative ions is going to be moving in this direction, right. Now, so we know that the charged ions do move when you apply an electric field, right. Now, similarly, you can also consider a charged particle, okay, say that I have a particle that is charged, okay, I can consider this as a macro ion, okay. So, now if I take Na plus, right, so the charge on that is your valency times E, right, where E is the fundamental elementary charge, right. So, in this case for Na plus, that is equal to plus 1 times E, right, that is your the charge on Na plus, okay. Now, if I have Ca2 plus, is going to be 2 times E, right. Similarly, if I have a macro ion, say that there are some 10 charges on the particle surface, okay. Therefore, I can say that there are 10 charges multiplied by E is going to be the charge on the particle, okay, if that's say Q. Now, in electrophoresis, what is actually exploited is the fact that if you have similar to ions, the particles have to be charged for it to move in a potential that you apply, right. Now, let us think about how does the particle acquire charge. So, I have a particle, okay, and that is charged. Any thoughts as to how the particles can be charged? Yeah, you have something to say? If you rub surfaces, the particles would get charged, right? I mean, that you would have, learnt in your, 10 plus 2 or something like that. But that would happen, that's because of friction, right? Now, if you have particles in solution, okay, now we are talking about particles that are dispersed in a fluid, okay, and I would like to have them to be charged. There are different mechanisms by which the particles can be charged, okay. One is that if I have a particle, okay, now the chemistry is so advanced that I can actually graft the particle surface, okay, I can actually put some charges on the particle surface, okay, I can maybe make the surface functionalized with some charges. Now, whenever I have particle like that, the moment I put it in water, what will happen is this particle with these surface groups, it gives COO minus, okay. This mechanism of charging a particle is by what is called as a surface charge dissociation, okay. You can buy particles like this, okay. If you want particle with any functional groups, you can get them in the market, okay. So, if I say, hey, I want a particle with the COOH groups on the surface, you can buy it, okay. So, therefore, one of the ways by which the particles can acquire charge is that you have a particle and there are some surface functionalization. This surface functionalization is done by putting some chemical molecules, right, molecules on the surface. The moment you put such particles in water, there is going to be some dissociation and that is going to leave a particle charge, okay. This is one mechanism. There are other mechanisms where if you have particles in a solution, if there are some ions in solution, okay, it could be H plus or OH minus or or Na plus or whatever, okay, then what could happen is your ions can go and get adsorbed on the particle surface. Okay, there could be a physical adsorption of ions on the particle surface. Okay, so this mechanism is something called as adsorption of ions, right. It could be adsorption of ions, it could be adsorption of any charged molecules, it could be adsorption of charged surfactants, it could be adsorption of charged polymers. Okay. So now that we have a charged particle, okay, and say that I am going to apply a potential difference, right. It's going to move, right, just similar to the ions that we talked about. Now if you apply an electric field E, okay, if you are applying electric field E, the force, the electrical force, or the force with which the particles move in the applied field is given by the charge Q times E. Okay, so you've done this at some point, right. If you have Coulomb's law, right, your force is Q1 Q2 by 4 pi r square, right. Now if you want, that's the force of attraction or repulsion between, of course there's 4 pi epsilon naught epsilon r, right, sorry, yeah, right. So okay, that's your, right. Now electric field is basically your force per unit charge, right, is Q, if you say Q1 Q2 instead of that, if you have Q squared, right. So let's say I'm going to do that. Okay, you have two charges, right. So Q divided by 4 pi epsilon naught epsilon r times r square, that's your electric field, right. That's a definition of, so that's how the force and the field are related, right. All of you know this, right? Yes? No? So basically the way the electric field is defined is, it's basically force per unit charge. Okay. So therefore if I'm saying that I'm applying an electric field E, okay, the force which the particles start moving either towards a positively charged electrode or a negatively charged electrode, okay, is given by FEQ, which is Q times E, and as I said, Q is the charge that the particle carries, okay, and we have been saying that I'm going to consider that this is a macro ion. So if I say that I have a particle surface with, like, say 10 charges, 10 dissociable groups, okay, your Q is going to be 10 times E, okay, but for in general you can call it as Q, which is the charge that the particle has, right. Now so of course if you didn't apply the electric field, the particle was moving because of the Brownian motion, right. Now that you applied a field, it's going to accelerate, right, it's going to start moving faster towards one of the electrode, okay, and how fast it moves depends on the strength of the applied field, right. Of course it cannot accelerate infinitely, right, because it is also going to feel the drag because of the presence of liquid. It's going to be slowed down, right, as it moves, okay, and ultimately it is going to start moving with some stationary or a constant velocity, and that constant velocity is basically determined by the balance between FEL and your drag force, right, because whenever you have a particle moving in the fluid, there is a drag force. Now the drag force basically opposes the motion, okay, ultimately there is going to be an equilibrium, and after that initial acceleration the particle slows down and it's going to start moving with a constant velocity, okay. Now, this FEL is Q times E, okay, and FD is your 6 pi RP times, mu times some velocity v, right? That is the velocity with which the particles would move, right, after that initial acceleration. Therefore, I can actually get what is v by E, which is the velocity which the particle is moving divided by the applied electric field, that basically goes as q divided by 6 pi rp into mu, right? Okay. This velocity per unit field is something called as is denoted by a quantity u, which is called as electrophoretic mobility. Okay, so the velocity which the particle is moving per divided by the field that you apply, okay, that velocity is what is called as electrophoretic mobility. And if you have a way of calculating what is the electrophoretic mobility, okay, you can, if you know the parameters of the particle and the fluid that you are using, I can actually calculate what is q, that is the charge on the particle. Okay, therefore, what people do is people exploit this concept called electrophoresis. That means the fact that I can set a charged particle into motion by applying electric field, I can exploit that to basically measure the charge of the particle. Okay, and again the experiments are going to be very similar. Okay, what they do is they will construct a rectangular cell, okay, that has two electrodes, okay, an anode and a cathode. You put a dilute dispersion of particles. The reason why dilute dispersion of particle is important is because it turns out that this expression that we wrote up, right, if FEL is equal to Q times E, is actually valid only under infinite dilution. That means the number of ions that you should have in solution, or the number of charged particles that you have in solution, should be very, very few, because if that's not the case, what is going to happen is, if there are a lot of particles next to each other, okay, the motion of one is going to be influenced by the other as well, right? So you would have to avoid that. Okay, so this kind of formalism is valid only if you're working with a very dilute cases, okay, where the concentration of ions in your solution is very, very less, or if you want to talk about colloidal particles, the particles, number of particles in your dispersion is going to be very, very few. Okay. Okay, so and the experiment that is done is, as I said, you take a rectangular cell, you put in two electrodes, okay, you put in a dilute dispersion. I can put this below a microscope. I apply a known electric field. Okay, that means I know what I'm applying. I know what is the E that I'm applying. Okay, now I'm recording a video of how the particle is moving. Because I can track particles, I can actually get what is the velocity with which the particle is moving, right? All I have to do is take different frames, I locate their position, and from that I can get what is the velocity with which the particle is moving. So therefore, I have some way of calculating the electrophoretic mobility. Okay, once I do that, okay, if I know if I have some other independent way of measuring the particle size, either by some using an electron microscope or some other means, I know RP. If I know what is the fluid that I am using, okay, I can basically calculate what is the electrophoretic mobility. Again, this is one of the very common techniques that everybody uses for measuring the charge on the particle.